Hello everyone. In this section, we are going to study the velocity of planetesimals. We have performed some orbital calculations of planetesimals and found that orbits are significantly modified when a planetesimal approaches another planetesimal. The strong gravitational interactions between planetesimals modify the orbit of a planetesimal within the Hill radius. It might be sufficient to consider two-pair interactions within the Hill radius because the gravity of a central star is weak within the Hill radius. So this is a review of two-body problems in the case of a hyperbolic orbit. Angular momentum is expressed L equals square root mu is a reduced mass, times g m sub 1 m sub 2 times a times e square minus 1. In the hyperbolic orbit, E is larger than 1. At the infinities, angular momentum is expressed mu bu. In the case of the energies, total energy of E is expressed g m sub 1 m sub 2 over 2a. At the infinities, we have only the kinetic energy of the 1 over 2 mu u squares. The scattering angle of the tangent theta over 2 is expressed g m sub 1 plus m sub 2 over bu squares. B is called the impact parameters. Asymptote cosine f sub a equal minus 1 over e. E is the eccentricities. Using this knowledge, we are going to find the velocity change in a single encounters. Direction of a relative velocity changes after the encounter of two planetesimals, while the magnitude of the relative velocity remains the same to satisfy the conservation of energies. So particle is approaching from this point with u and is moving to u. Decompose to the parallel component and the perpendicular component. Actually this angle is theta. Then this becomes u cosine theta. This part is u sine theta. Change of the parallel component is expressed. So u cosine theta minus u cosine theta minus 1. Use a double angle formula for the trigonometric function of the cosines. Then it becomes minus 2u sine squares theta over 2. In the perpendicular component, there is no perpendicular component before the encounters. So increase of the perpendicular component is expressed u sine theta. So we'd like to find out the sine theta and the sine square theta over 2. So we start with the equation for the angular momentums. L is equal to square root mu g m sub 1 m sub 2 a e square minus 1 is equal to mu bu. Now take a square in the both sides. The 1 over u is cancelled out. Then for the case of the energy is equal to the g m sub 1 m sub 2 over 2a equal 1 over 2 mu u squares. So from this mu u squares is expressed g m sub 1 m sub 2 over a. Then you can substitute mu u squares into this expression. Then it becomes b squared g m sub 1 m sub 2 over a. G m sub 1 m sub 2 appears, so it's going to be cancelled out. So we have an expression for the e squares. E squares can be expressed b square over a square plus 1. And the e becomes larger than 1. So from these equations, b square over a square is expressed e square minus 1. Then we'd like to express the sine theta over 2 and the sine theta. For the case of the sine theta over 2, theta expressed 2f sub a minus pi. And also you can use a cosine fa equal minus 1 over e. So sine theta over 2 is expressed sine f sub a minus pi over 2. It becomes minus cosine f sub a. This is 1 over e. You can use this relation equal 1 over square root 1 plus b squares over a squares. For the a squares, you can substitute this expression is here. So it becomes 1 over square root 1 plus b u squares over g m sub 1 plus m sub 2 squared. So this is sine theta over 2. So change of the parallel component is expressed minus 2u sine square theta over 2. So it becomes minus 2u 1 over 1 plus bu squares over g m sub 1 plus m sub 2 squares. This is a change of the parallel component of the u. For the perpendicular component, we need to calculate sine theta. Sine theta can be expressed sine 2f sub a minus pi. So it becomes minus sine 2f sub a. Then you can use the double angle formulas. Minus 2 sine f sub a cosine f sub a. So it becomes minus 2 square root 1 minus cosine f sub a squares. Cosine f sub a. So it becomes 2 over e squares. Square root e square minus 1 because cosine f sub a equal minus 1 over e. Then you can substitute e. It becomes 2 over 1 plus b over a squares. B over a. Then you can substitute a into this expression. It becomes 2 bu squares over g m sub 1 plus m sub 2 over 1 plus bu squares over g m sub 1 plus m sub 2 squares. Then delta u, change of the perpendicular, is expressed u sine theta. Then you can substitute this expression here to find the change of the perpendicular component of the u during the single encounter with another planetesimals. We have found the change of the relative velocity of a planetesimal during single encounters, but the planetesimal frequently meets a number of planetesimals and changes its velocities. A planetesimal with mass of the capital M and the velocity of the v sub m encounters many planetesimals with a mass of the m. This orange circle has a mass of the m at the rest, so velocity is 0. So initial relative velocity is expressed as v sub m. Perpendicular component of the v sub m with respect to the initial velocity is summed up to become nearly 0 after encounters with many planetesimals, sometimes moving up and sometimes moving down. On the average, we expect it to become 0, while the parallel component changes with time. Then we'd like to sum up all the contribution of each encounter with the planetesimals. We'd like to find out how many particles actually encounters with the planetesimal. So nu times 2 pi b dB is the number of planetesimal with the mass of the m that encounter with the planetesimal with the mass of the capital M. So this is how many planetesimals are encounter with the target planetesimal with the mass of the capital M. And the change of the parallel component v sub m during a single encounters, you need to multiply. Then if you sum up the change of the velocities for the single encounters, and you can find the total change of the velocity of a planetesimal with a mass of the capital M. For the single encounters, delta v sub m parallel equal m over m plus capital M times delta u parallel. So at first, I'd like to derive this expression. We consider two particles. M, position vector, is expressed r sub m. And the target planetesimal capital M. Position vector r sub capital M. R is expressed r sub m minus r sub lowercase of the m. This is center of mass. So center of mass is expressed m times r sub m plus m r sub m over m plus m. So from this expressions, you can find the position vector for the large particles. R plus m over m plus m, relative vector of the lower case of the r vectors. So from this equation, you can find the derivative with respect to times. So V sub m is expressed as V plus m over m plus m V. So from this equation, you can find the change of V sub m during a single encounters. So delta V sub m equals delta V plus m over m plus m delta V. Actually, the center of mass doesn't move, so delta capital V equals 0. So delta V sub m equals m over capital M plus m delta V. So we can find out the relation between the relative velocity with the velocity of the planetesimal with the mass of the capital M. And we derived this expression. Then you can substitute here. We have already derived the delta U parallel. Then it becomes this equation. Then you can perform the integral with respect to B. So it becomes this expression. A planetesimal loses its kinetic energy as it encounters other planetesimals because of the negative signs. Speed of the planetesimal is decreasing with times. This process is called dynamical frictions. Then we'd like to estimate the time scale for the dynamical frictions, change of the velocity due to the gravitational interaction with the other planetesimals. We call relaxation times. A planetesimal interacts with other planetesimals gravitationally. The time scale of the relaxation is estimated. T sub relax equals V sub m over dm sub m over dt's. You can substitute dm dt's into the equation. You have this expression. We consider a system composed of many planetesimals with equal mass. Then, instead of the capital M, we use all the particles have the same mass of the lower case of the m. And the sigma sub m is expressed m times n times the scale height of the two HMs. HM can be calculated V sub m over omega. Then using this expression, relaxation time of the tau sub relax equals to the V sub m to the fourth over 2 pi g square log lambda square plus 1 times m omega sigma sub m. So this is the relaxation times. Then viscous terrain and gas drag. A planetesimal interact with other planetesimals under the gravity of a central stars and then increases velocities. The increase in the velocity is due to the gravitational potential energy of a central stars. This is called a viscous terrain. On the other hand, a planetesimal loses its velocities due to the gas drag acting on it. Change of the velocity due to the gas drag dv sub m over dt is expressed as minus v sub m over m v sub m over fd's. So use the Stokes numbers is expressed minus v sub m omega over Stokes numbers. And then we can estimate equilibrium velocities. Time scale of the relaxation is estimated as that tau sub gas is equal to v sub m over dv sub m over dt's. So using the previous equations we derived is Stokes number over omegas. So equilibrium velocity of a planetesimal is calculated from the tau sub relax equal tau sub gas. Then v sub m can be calculated 9.3 meter per second when the mass of the planetesimal is 10 to 15 kilograms. The velocity is increasing with mass of the planetesimal. The velocity of a heavy planetesimal with mass of capital M is suppressed by dynamical frictions of small planetesimal with mass of the lower case of the m. We find the velocity distribution of planetesimals by considering the energy is equally distributed among the planetesimals. So last factor is attached to expressed energy is equally distributed among the planetesimals. So we consider the kinetic energy of the 1 over 2 mv square is constant. We could use the equilibrium velocity to estimate the growth rate of planetesimals. So in the next sections, we are going to study the growth rate of a planetesimal in a disk. Okay, this is the end of this session.